Picture a volcano erupting. As the smoke and ash balloon upward and outward, the sky darkens, turning day into night. Bolts of lightning briefly flicker in the darkness all around, while thunder seems to shake the ground just as much as the seismic rumblings happening deep below the earth. We tend to think of weather as being hyper-localized, like it's raining in western Washington while eastern Washington is bone dry, or there's a blizzard in Buffalo, New York, while New York City is cold but unaffected. But in fact, our weather system is a global network of interrelated events. And when it comes to volcanoes, those events are experienced everywhere. You may live far away from the lava flows of an active volcano, but the impacts of that volcano's eruption are felt around the world. Volcanic ash isn't like ash from a campfire. It consists of tiny bits of jagged rock, microscopic mineral dust, and even volcanic glass. Those particulates range in size, from grains of sand on the larger end of the scale, down to a fine powdery dust on the smaller end. And when those particles billow upwards into the atmosphere, it can cause massive weather changes. Some eruptions can even reach the stratosphere. Volcanic eruptions feel primordial. They're the phenomena that built and shaped our planet, and they do some really interesting things. When all those ash and rock particles crash into each other in the air, they often separate charges just like ice particles do in a normal cloud, producing a phenomenon known as volcanic lightning. But it doesn't stop there. An eruption can also produce massive plumes of sulfur dioxide. When those gas and particle clouds are big enough, they can travel the world. Here in the US, many people remember the 1980 eruption of Mount St. Helens. Its eruption was so powerful that it changed the courses of rivers nearby and pumped billions of cubic yards of volcanic ash 14 miles into the sky. 57 people died from that eruption, and thousands of people across the Pacific Northwest were impacted by the event. Within 2 to 3 days, traces of the ash cloud at Mount St. Helens reached the East Coast, and within 2 weeks, those ash clouds had drifted all the way around the planet. But 220 years ago, in the year 1815, the Earth experienced the most powerful volcanic eruption in recorded history. The Tambora eruption in Indonesia unleashed a staggering 80 times more ash than Mount St. Helens. It's not hard to imagine how quickly that ash cloud spread globally. And the sulfur and ash that eruption generated actually changed weather patterns for the entire planet. It reduced incident sunlight across the surface of the Earth in what came to be known as the year without a summer. Crops withered and died. Famine and disease spread. At a time when the world wasn't yet connected by the internet, and the telephone wouldn't even be invented for another 61 years, it's not hard to picture this event leading to global panic. People who lived thousands of miles away from the volcano, who knew nothing about its eruption, suddenly saw ruby red sunsets in the sky every night and snow falling in June. Was this a biblical or mythological event? Were the gods angry with humanity? The effects were felt everywhere, though some regions were less impacted than others. Even here in the United States, thousands of miles away from the Tambora volcano, the end result of its eruption reshaped our country. I'm Brian Pietrus, Emily Gracey's associate producer. This week, Emily and I are chatting with Dr. Kevin Anchukaitis. He's a dendrochronologist, climate scientist, and paleoclimatologist at the University of Arizona. He'll be telling us more about this unbelievable volcanic eruption, the various ways paleoclimatologists can study events like this from the past, and how the Tambora eruption rippled out into unexpected places like art and agriculture.
Kevin Anchukaitis, so nice to meet you. This is a really fascinating, interdisciplinary topic because I feel like it's pulling in all of these different things. But of course, we're a weather show, so we want to hear about the weather and climate portion of it as well. But can you give me a little brief background on you and what your area of expertise is?
Yeah, sure. So I'm a paleoclimatologist, which means I study the climate of the past. My usual way of doing that is using the annual rings of trees. So I'm a dendrochronologist as well. And a lot of my work does focus on things like the sort of past human response, past civilization response to climate extremes, including those that are caused by volcanoes. So this is this sort of interdisciplinary approach you're describing is right up my alley.
Yeah, totally. And then like in addition to like the human factor, there's a lot of chemistry going on in this as well, like atmospheric chemistry. So we'll dig into all of that. But as we wrap up summer here, we want to hear about this one year, many years ago, where they call it the year without summer, but this all stems from a volcanic eruption, correct?
That's right. Yeah. So we associate this year without a summer with an eruption that happened for most of the places we're talking about that didn't have a summer, half a world away.
Is this typical? There's an eruption and then it takes a whole year for this to kind of go up in the atmosphere. Take me through each step of from eruption to all of a sudden people are not experiencing summer.
Right. Yeah. So we actually see this quite a bit with large tropical eruptions, which included Tambora in basically late spring of 1815. But generally what you're seeing, right, is that you get a volcanic eruption, you get this buildup of magma and gases below the volcano. And when that pressure exceeds what can be held by the surrounding rock, you get these eruptions. Now, you need a couple things to happen, though, for this eruption to actually affect the weather in the following year. One, you need to get this material way up into the stratosphere, right? So basically, you need it well above where our sort of typical planes fly. So you need to get it way up there first. That's the first requirement. Second, you need that material that's been lofted way up into the atmosphere to have a good quantity of sulfur in it. It turns out, and we've sort of discovered this relatively recently, so this comes about through research after Pinatubo and in the sort of later 1900s. When I put it that way, that sounds like a long time ago. We know that it's really the sulfur doing the work of reducing the amount of energy in the Earth system. So what happens is if you get that sulfur up in the atmosphere, you can have this chain of chemical reactions you talked about. So first we have like sulfur dioxide, right? So some gas, it's got some sulfur, it's got some oxygen, it's in this sort of gaseous phase. You can, when it's up there in the atmosphere, you can start to go through these chemical reactions of basically oxidizing and having it interact with oxygen and hydrogen. And so you get actually sulfuric acid on the way to what we call sulfate, so SO4. And this is the material of sulfur that can take on this aerosol form. So imagine taking a can of spray paint, sort of spraying it in the air, right? And it doesn't fall out immediately, right? You sort of can see these liquid droplets. And this is what we're sort of talking about is these very, very small droplets that turn out to be really important because they can block out incoming solar radiation, basically reduce the amount of energy that's coming into the Earth system that actually makes it through to the surface. And that energy, of course, is what keeps us warm. And so when that sulfur and that sulfate aerosol is sort of hanging out up there, way up in the atmosphere, it can actually reduce the energy in the Earth system. Now, because it's way up there, right, it's above our weather. So it's not getting rained out. It's not settling out really easily. And so it stays up there for, a year or two, maybe more, and then spreads out from the tropics. And so with a tropical eruption, you can actually affect weather and climate in both hemispheres, right? Because that material moves towards both poles, moves towards southern South America and northern North America and Europe. And that can take some time until that sort of veil of sulfur is sort of doing enough blocking of the incoming solar radiation to actually affect sort of climate down here at the surface where we are. Eventually it does fall out. Some of it falls out over Greenland and Antarctica. And then ice core scientists who we work with go take long cores of ice. And one of the things they see in those ice cores are these sulfate spikes, these spikes of sulfur material that got there by transport all the way from the inside of a volcano through the stratosphere and then back down to those ice cores. And that's one of the ways we know about past volcanic eruptions before there were historical records.
Okay. But you study tree rings typically, right?
That's right. Yeah.
Is there evidence in the tree rings too?
Yeah. So when we're looking at tree rings for evidence of past volcanic eruptions, what we're mostly looking for are the climatic effects. Although, if you happen to be sort of fortunate and you find a tree near where a volcanic eruption occurred, you can maybe see the direct effects, and I can talk about that too. But most of the work I do is looking at the climate effects of these eruptions. And so if we go up way into the northern hemisphere, all the way up to tree line, where you start to run out of trees and it turns into tundra, you can find trees that are incredibly sensitive to variations in temperature, right? They're sort of just hanging on at those really high, cold, short growing season locations. And those trees will hold in their rings a record of past temperature, and including the cooling that follows a volcanic eruption. And so what we can do is we can go and take samples from these trees. We can look at the width of the rings, or even the nature of the wood, the density of the cells that make up those rings. And we can actually reconstruct past temperatures. And what we see consistently is that after these large eruptions, these large sulfur-rich eruptions, particularly the ones we see in the tropics, we can see a temperature depression of a year, sometimes 2 or more, depending on the strength of the eruption, that those trees recorded. And so this allows us to go back in time before there were thermometers, before there were people writing these things down as they were written down for Tambora. And we can reconstruct how the climate system responds to these eruptions.
Wow. Okay, so the tree ring people are meeting up with the ice core people, making this connection. When was this discovered? How long has this been known, this connection between the two?
There's work as early as the 1970s and 1980s, sort of putting this connection together. Pinatubo, the sort of most recent big eruption, doesn't happen until the 1990s, early 1990s. But there are, these ice core scientists, there are people looking at past temperatures, but start to kind of put this record together, right? It's spotty at first, not many eruptions, not many temperature reconstructions. But by the 1980s and certainly into the 1990s, you have more and more people taking larger and larger data sets of tree rings, temperature sensitive tree rings, and more ice core and more precise dating of those sulfur events in the ice cores to make this connection. So we've sort of known about this solidly since, I'd say, the 1990s.
Is it something you can look at with recent eruptions, or is it like not necessary because we have temperature data?
You can see it for recent eruptions, but yeah, we have satellites and we have good temperature data. So we sort of have a good idea of what happens after, say, Pinatubo or El Chichon in Mexico. We have a pretty good record of those. But when you think about volcanic eruptions, right, these are, especially big ones, these are by definition rare. Right? We don't see a lot. In fact, our last big one was in the 1990s. And so, we don't have a lot of examples to study. And in fact, a lot of what we know about how volcanic material behaves in the atmosphere, this sulfate process I talked about, comes just from Pinatubo. And so in order to sort of increase our sample size, right, get more data, we can wait for the next eruption. A lot of us are, right? We're ready to go. When it happens, we're ready to watch the climate and how the trees respond. Not hoping for it. No. But we're ready when it happens. But beyond sort of waiting for the next one, what we do is we go back into the past. And yeah, this is where the ice core people and the geologists and the tree ring folks and the historians and the archaeologists, we all get together quite literally and talk about these things and try and piece together all this different lines of evidence.
Do the geoengineering people ever want to get in on the conversation and learn how this works?
There are definitely connections between the geoengineering community and the sort of climate, volcano, past climate folks. A lot of geoengineering work thus far has been in computer models, right? That you spin up a simulation of the Earth system, and then you do something like say, okay, what if I, in this computer simulation, it's sort of like playing Sim Earth. What if I add all of this sulfur material to my simulated stratosphere? Let's see what happens to my simulated surface. It's really important that we have conversations between that, what's largely a modeling community, and the folks like me and my colleagues that are looking at these past eruptions, because we really want to know how good these models are at capturing what can be a fairly complex system with a lot of variables that are tough to control, right? The direction of winds and airflow in the stratosphere, right? So my sense of this is that models are not quite there in terms of simulating the full range of behavior that we see when we go back in time and examine past large volcanic eruptions. And I think that should give us a lot of pause, that if we are using models to anticipate what might happen through sort of a human volcano of sulfur, right, of this sort of geoengineering, that we better be sure those models are capturing all of this nuance that we see and all this variability. It's not a simple one-to-one where you say, right, this amount of sulfur, volcano at this latitude, boom, that's how cold it gets. It's really much more complicated because the Earth system is more complicated.
Mm. Okay, let's go back to the year without summer. When you say the temperature was depressed, how much are we talking here?
Yeah, it's tough to say globally because even with our tree rings, we don't have a full coverage of the globe. And trees also preferentially record sort of summer temperatures. That said, we think that Northern Hemisphere summer in 1816, the year without a summer, could have been as much as a degree Celsius cooler. And now this varied a lot in space. There are other estimates that put it a bit lower, but we're talking something that we can notice in the tree ring record and even very clearly in the sort of limited thermometer data that's available.
And then how does 1 degree Celsius kind of play out? It doesn't sound like much, right? So
right.
What does that mean?
Right. So that's this big average. It's like, well, what does that number really mean, right? And so the way it plays out is in terms of weather, right? If we think about climate as the sort of, if you will, the statistics weather or maybe in more simple terms, the average of weather. What does that actually mean on the surface? And what that means is that you would have had many more days, extended periods of time that could have been many, many degrees below normal. And so we know this, and one of the ways that the 1816 gets its name, the year without a summer, is from New England here in the U.S. Because there are long thermometer records in New Haven, at Blue Hill. And so we actually have thermometer records that give us sort of a quantitative estimate. But we also have weather observations. And so, for instance, we know that it snowed in 1816 in upstate New York in early June, that there were killing frosts throughout that summer. And so you're exactly right. That sort of, hemisphere summer average of a degree. Oh, what does that mean? Well, that manifests in the ground, on the ground as, things like summer snowstorms. For instance, we know that in Switzerland, the sort of average temperature during that summer in the Alps and in Geneva, for instance, is more like 4 or 5 or 6 degrees Fahrenheit cooler. And so that is the kind of thing that, we actually experience. We don't experience this large hemisphere multi-month average. We see things like dark and cold weeks in Geneva, or we see snow in the summer in New England. And that's where you really start to see these human impacts.
It sounds so much like what we deal with like this summer when it comes to climate change, where people say, well, a degree isn't that much of a difference. But then there's this overall theme of like heat waves or, wildfires that have this impact.
That's exactly it. And to put it in some context, we know that during the sort of coldest period of the last ice age, right, about 20,000-ish years ago, when Manhattan is covered in a very deep ice sheet, right? And these places that we're talking about in New England are entirely under kilometers of ice. That's a global temperature depression of about 6 degrees Celsius.
Wow.
So these averages are sort of tough to think about. These long-term, large-scale, season-long averages are sort of tough to think about. But it only takes 6 degrees of global cooling to turn us into an ice-covered, lower sea level by 100 meters planet. So these small differences in these averages, right, can actually translate into big differences on the ground in local places.
So what does that mean for humans? How do we feel 1 degree Celsius difference? Like, I guess particular to that year, like in 1816, what did they notice? Yeah.
So, the things I think that are most obvious to people are the weather they experience, but also how the environment around them is responding, right? We can go inside, we can light a fire, we can put on a sweater, or these days turn on the air conditioning. But in the environment around you, you're going to see these impacts as they accumulate. So, for instance, in New England and Western Europe, what you would have seen is crop failures, right? So extensive agriculture that didn't produce at all. The main crops just dying mostly of frost or cold. And those would have been things that would have been very obvious in the early 1800s on a New England landscape, or in Western Europe, in the UK, in Ireland, for instance. This sort of response of the agricultural landscape. People would know that it's not normal to have snow in Albany, New York, in June. They would have seen that, and they knew that. The writings of the time make note of how unusual and remarkable and kind of awful this is. And so people knew something was unusual, but the way it really stands out, I think, to folks is in these weather events that accumulate and give us those averages. And then in the way that these consequences accumulate in sort of the natural world, and particularly to the extent that we've engineered the natural world to provide food for us.
I had read about how there was kind of within North America, there was a lot of movement west out of New England around that time. Is that correlated to the year without a summer and all the crop failures? Is that kind of responsible for that like westward expansion that America had around that time?
Yeah, there seems to be some consensus with historians, environmental historians, and historians of the era that this was one contributing factor. That you're already practicing agriculture in a somewhat sort of marginal environment for sort of large scale agriculture, particularly in the early 1800s when it was sort of globally colder. And so, this would have been one of the things that one of the shocks that would have worked its way through the system to emphasize, hey, there may be better, more stable places for us to carry out large scale agriculture. So it wasn't the only effect. Obviously, there's a lot of things going on in Europe and the US at the time in terms of technological change and societal change. There's economics that come into play in New England. For instance, what we know is that while Canada also suffered from the consequences of this weather, you don't really see the sort of hunger and famine there that you saw elsewhere, largely because they had prohibited the export of what grain was available, right? And so what this starts to tell you is that it's not that humans, even back in the 1800s, let alone now, are sort of, just simply at mercy of the weather or the climate. A lot of the ways that we either are resilient to these weather shocks or climate changes or not, and vulnerable, has to do with sort of economic and social frameworks and conditions. And you see that for Tambora in Europe as well at the same time. So, but that does seem to be something I've seen quite a bit, that seems to be, one of the factors in westward expansion, or at least movement of agriculture out sort of New England and elsewhere.
Was the Midwest and westward less impacted, or was it just that there wasn't agriculture at that kind of scale agriculture there, and they just thought this must be better?
Yeah, that's a great question. So as far as we can tell, the temperature consequences of this were felt much more to sort of New England and Northeast, and that what records we have, for the Midwest, it's a little less certain. But we evidence would suggest that these colder temperatures didn't reach Western U.S., Western North America, and that this was fairly sort of focused on higher latitudes and sort of the circum-Atlantic region. What other areas might have had this cold, we don't have as good of an idea because we don't have the same kind of records. But it seems that while everywhere was sort of a bit colder during the period of the early 1800s, that real sort of like punctuated year without a summer was a New England effect and didn't have as much reach to the West.
I read too that there was a lot of like art and writings that came out of this summer. So I'm curious, as a scientist, do you read these things? Do you look at art when you're studying science?
I mean, I love to start my presentations that I give with a piece of art and try and sort of have it be relevant. So I've got paintings from, say, Italy of volcanic eruptions there that the people have made. And you're right. There has been sort of, speculation, I'll call it that, that some of the art and writing of the time reflects this year without a summer. And we do have written records of the skies, particularly in New England, having this sort of reddish haze that didn't go away. The fact that it didn't go away when it rained is a sign that it was up in the stratosphere. And so it was interfering with the sun from there. We know that this year without a summer was not only cold but rainy in, say, Western Europe. And so you can imagine sort of dark storm clouds over Lake Geneva, for instance, as Lord Byron and Mary Shelley and her husband are sort of spending the summer writing inside in an inhospitable Geneva. But I think, the other thing to keep in mind, right, is that particularly for the case of Mary Shelley and Frankenstein, and sort of Europe in general, there's a lot of things happening in Europe at this time, right? In the early 1800s, there's a move towards mechanization. There are riots. This is when we learn sort of about the Luddites and this sort of, big scale change that's happening in sort of labor and at sort of the dawn of the 1800s. This is at the end of the Napoleonic Wars. And so, you've seen millions of people die and Europe being in upheaval during the Napoleonic Wars. Soldiers returning from those wars and coming back from these communities. And so, there would have been a lot of disruption and a lot of sort of recent history to draw upon for the poetry and literature and art that comes out at this time. So my sense is that it's not so simple, right? That it was probably, true that Mary Shelley got more writing done in the summer of 1816 because it wasn't particularly always nice to go outside. And so I said, well, we might as well write a world-changing piece of science fiction. But there would have been a lot of sort of things that she would have drawn on probably. Maybe the sort of gloomy summer in Geneva being one of them.
So calling Frankenstein a climate refugee might be a little bit of a stretch.
Yeah, I think that's pushing it. It's a good story. It's a good story, right? You want this to be this connection, right?
Right.
And it's tough to say how much influence that would have had, but I think we do always, when we think about these climate shocks, is to remember that they are one of, sometimes very important, but one of many factors that humans are dealing with at any given moment. And those things filter through into our mind and into our art and into the way we live, in various different ways. But it's a good story. It's a great story.
Yeah, I'll hold on to it.
Yeah.
On the topic of art and climate science like that, I remember seeing a display a couple of years ago. I think it was at the LACMA Museum about the Little Ice Age and how art around that time is kind of how we now, looking back, know like this was an exceptionally cold winter, things like that. I was just curious, like, how does this The Year Without a Summer compare to the Little Ice Age that happened back then?
No, that's a great question. So in the early 1800s, you have not only the Tambora eruption, but you have another eruption that occurs in 1809. We're not sure where the volcano was. We know there's an eruption. We see it in the ice cores. We see the response in the tree rings. We're not sure where the eruption was, though. Persistent mystery now for several decades, despite our efforts to try and solve it. But the early 1800s are generally cold already, even before the eruption of Tambora. So Tambora occurs and makes things cold, but it makes things colder during a period of the end of what we would call the Little Ice Age. And so you're talking about one of the colder times, probably globally and in the Northern Hemisphere, of the last millennium, of the last 1,000 years. And we associate the Little Ice Age with a couple things, but one of them is volcanoes. There's basically a series of volcanoes starting in sort of the late 1200s, but certainly vigorously in the middle of the 1400s. And they come with some frequency. And using climate models, we can show that one of the reasons we can sort of pick out this period from sort of the 1400s to the middle 1800s as a sort of Little Ice Age. And that's not a term everyone loves. But the reason we can sort of spot that in global temperature reconstructions as a period of colder conditions is largely because of the presence of these volcanoes. The sun was a little dimmer for periods of time, what we call solar minima. But probably the primary factor in sort of the relatively cold periods that lasted for those, several hundred years was volcanoes. And really, coming into 1809, 1815, a few others that happened in the 1800s. But these were major factors in sort of, reducing global temperatures by several tenths of a degree, again, on average.
Using some of those kind of predictive models that you talked about, is there any way to sort of, for lack of better words, like forecast if we're at risk for that in our lifetimes happening again? And is there, anything that can kind of be done to offset that or prevent, the effects of that being as devastating as they have been in the past, especially like agricultural?
Yeah, so that's a really good question. So people have done this. They've sort of run our climate models into the future. And the way this is done is that you have a couple different scenarios. You say, okay, humanity gets its act together. We convert to renewable non-carbon energy sources. And, this is what sort of the trajectory of atmospheric CO2 looks like. And then we can sort of tell the model, hey, here's what atmospheric CO2 is. And then you have another scenario where you say, oh, we go and find every bit of dirty coal and, every really difficult to extract fossil fuel deposit, and we dig it up and we burn it. And that gives us a, much higher trajectory of CO2, and you tell the model that. And so this is the way we sort of, project forward to say, all right, what will temperatures be like in 100 years? Well, you can do those same experiments, and then you can basically set off a volcano in the computer, right? You say, hey, in addition to atmospheric CO2, we're going to put a bunch of sulfur in the year 2050 from a tropical source. There's going to be this much sulfur. It's going to be lofted this high. Those sulfate particles have this characteristic. You tell the computer all that and you let it run, and you can see what happens. And when you do this, you do see several years of temperature depressions. And people even have done this with 2 eruptions. So you do get colder periods. But what you have to realize is that the whole time that we've been sort of heading towards that simulated eruption at 2050, we've been adding tremendous amounts of CO2 and methane to the atmosphere. And so really future volcanic eruptions are important in getting sort of accurate projections 100 years out, because they can sort of disrupt that sort of warming trajectory. But we never even return in an eruption to the kind of pre-industrial temperatures we had, say, in the sort of late 1800s or early 1900s. That it is important for getting good projections, but it really is sort of a blip compared to, particularly these high emission scenarios that take us to, say, 3 or even 4 degrees Celsius warmer by the end of this century. So people are worried about this, and there's actually some interesting effects that happen that would change how volcanoes actually modify surface climate. And one of those is, all right, so you're adding all this CO2, you're adding all this energy down where we here are in the troposphere and where your weather is. And what that does is it actually lifts the boundary between where the troposphere and the stratosphere are. And so that boundary goes up. And so now, your eruption has to get higher, and that injection physics changes. And so Thomas Aubrey, who has worked a lot on sort of thinking about future volcanic eruptions, one of the things he's done is actually look at how plume dynamics change just because you increase CO2 and warm up the troposphere and change those troposphere stratosphere dynamics. So that's an interesting little effect. But really what you see in these models is that that CO2 is so dominant that, we don't go back to sort of a little ice age type of environment, even with sort of multiple eruptions of Tambora size.
So we're modifying our climate more than any future volcanic eruption could.
We are doing it so fast. We are modifying climate so fast. CO2 is rising so fast that we are a geological agent. On the order of things that have happened deep in the geological past that have released CO2. So,
are there though any ticking time bombs when it comes to volcanoes that you're just watching because they're kind of overdue for that kind of eruption?
Not any particular volcanoes. We are sort of it's been a long time since we've had a very large climatically effective eruption. We do look to the tropics for a lot of these potentially climatically important ones because, we have seen eruptions in, say, Iceland, in Hawaii. There was just several out sort of in Alaska slash Eastern Russia that followed the large earthquake that was there. But these are not climatically active. They're not getting enough sulfur up into the atmosphere. So you really look to these more sulfur-rich tropical volcanoes as probably the ones that are most likely. And that includes in Indonesia, where the 1815 eruption is. There's a number of volcanoes from the record that are in sort of the western sort of tropical Pacific, Indo-Pacific region. And so that is one region I would look to for a future climatically important eruption, just like the one that in 1815.
You mentioned that you've been traveling for some research lately. Can you share any of that information with us on what you're working on?
Yeah, the timing was really good. So I was in Alaska and Canada, and I was 3 weeks in the Arctic, and we were way up at northern tree line. So basically where you run out of forests and you have your last few trees before you get into the tundra environment and shrubs and things like that. And one of the reasons we're there is because we are studying volcanic eruptions in the past. We know about sort of big past eruptions and their climate consequences. So 1601 is a cold year because of an eruption in 1600. There's a big eruption that happens also in Indonesia, in the Western Indo-Pacific, in 1257. And we're trying to go back and look at these eruptions and understand better how they change surface climate. Like I said, everything that these records, these combinations of tree rings for the temperature effect and ice cores for the sort of atmospheric effect and the chemistry and the timing of these eruptions, says to us that it's not a simple linear relationship. You can't sort of say, okay, this amount of sulfur leads to this much cooling, that there are complications. And we're trying to understand those complications, right? We're trying to understand, well, why is 1601 so cold? In fact, in many of the reconstructions I've worked on, it's the coldest year of the last millennium, even colder than 1816. Why is that? It was an eruption. It was a sulfur-rich eruption, but it wasn't larger, say, than the one in 1257. And so why do we get severe cooling with some eruptions and then less cooling with others? And so, that's an important question because that's not something models are super happy to do. Usually in models, it's like, all right, lots of sulfur, it gets colder, right? And the Earth seems to be more complicated than that. So we've been at northern tree line in North America looking for more evidence of these eruptions. And recently what we've been doing with this new material that we gathered way north in Alaska and sort of way central North Canada is actually looking at the individual cells in rings. If you think about it, the way that sort of rings form is they're a collection of these cells. The more cells that a tree puts on, the wider ring. But also, particularly the last few cells of the year are very sensitive to the climate conditions at the end of the year. And we found that by going in and making cellular level measurements, we actually can get even more accurate summer temperatures. We can also do things like parse the length, say, of a cooling period. So instead of saying, right, the ring for 1816 shows that it's cold in the summer, we can actually go in and say, oh, it doesn't get cold until very late summer. Let's say just August instead of July and August. And this can reveal something about how these, decreases in sunlight that come from the eruption work their way into sort of local weather, right? Is it 2 weeks? Is it 3 weeks? Is it 4 weeks of cold? That starts to become important to this understanding of how the volcanic climatic influences arrive at a particular location or particular region, in the way that we're talking about for the year without a summer in 1816, right? This place in New England and this week or this set of weeks had this particularly cold experience. What is it that combines with the reduction in sunlight to give us these sort of focal points and these times of real severe weather?
Wow, interesting stuff.
Yeah, it's fun work.
It's been quite a few years since I was in science class, but I remember I took a paleoecology class talking about the Yellowstone supervolcano as a possible eruption, probably not in our lifetime, but I think it's something like a couple 100,000 years overdue historically. Is that something that you worry about, or do you see that as not really being something we'll have to worry about for the, subsequent 1,000 years or something like that.
Yeah. So there've been super eruptions, like Yellowstone. There's one in basically where Mammoth, California is right now. There was a big eruption that also spread sort of volcanic material over half of North America. So we see evidence of these, even in the recent, relatively recent geological past. In terms of things I worry about, though, it's relatively low on the scale. These things are very rare. All of these sort of caldera regions are really well monitored. And, when it comes to volcanoes, there's not really sort of an overdue. You can say, oh, well, there's evidence of eruptions on average every 700,000 years or something, right? But then you look and it's like, well, we had 3, and that average reflects anything from a shorter period to a much longer period, right? And here's another time where those averages don't necessarily do us any favors. So with volcanoes, there's not necessarily an overdue, if you will. So, we're geologists are aware of them. We're monitoring sites that could potentially have those kind of very high volume, long-term eruptions that we see in the geological past, but it's down there on my list of concerns right now.
Well, Kevin, thank you so much for your time today. This was really interesting stuff, and so impressed by all of these different subjects that you're knowledgeable in.
This is one of the great things about being a paleoclimatologist is it's never boring. And you get to ask really cool questions about specific events and work with really cool people who do, who bring all these pieces together, right? I've never been to Greenland or Antarctica, but because I've got colleagues that have, and because they know how to get these volcanic records out of those ice cores that they collected, we can do this really cool work. And they've never cored a tropical tree. So, it's a good combination of skills and experience.
I'm picturing like a really fun party with the tree ring people and the ice core people.
Oh yeah, we're the coolest. Yeah, the coral people are pretty cool too. So yeah.
Off the Radar is a production of the National Weather Desk. Make sure you're following the show on Apple Podcasts, Spotify, or wherever you listen to podcasts. New episodes publish every Tuesday. We have some great episodes coming up for the rest of this month. We're getting seasonal with fall foliage forecasting and getting a sneak peek of the upcoming winter outlook. Thank you to Dr. Kevin Anchukaitis from the University of Arizona for joining us this week. This episode was a joint effort in producing, editing, and hosting with Brian Pietrus and myself. Thanks to the National Weather Desk and Sinclair Broadcast Group for their ongoing support of the podcast. I'm meteorologist Emily Gracey. Make it a great day.